How about now? Yeah, great. Thank you. So welcome to the second half of the term. Chronologically, it has been the second half for a while, but, second half starts after the midterm. I will go through a few announcements rather rapidly. You guys did fine. The reason you don't have your exams back yet is a couple of people wrote in pale blue ink that doesn't scan. It's like that secret ink, which if you write on a document and then photocopy it, it doesn't get photocopied. So we have to go through and grade a couple by hand and be ready. The class did just fine. We will post tomorrow the distribution of scores, the answers, the regrading policy, and so on. After you have seen your exams on Wednesday, we'll talk a little bit more. From my perspective, there were really no surprises. There was one question on the exam which I knew involved a subtle combination of concepts, and not surprisingly, that one turned out to be the one where the answers were a little bit all over the place. But all the others were done about equally well or badly, from what I can tell. But we'll know more. The other people did just fine. The distribution, from what I saw, and I haven't looked carefully yet, has a left-hand tail. So the 30s, 40s is where the bulk is, and then there's a sort of long, thin tail down. There is a typical performance of a class that has done well. I would implore those of you who are just out of high school to put away in your heads this idea that you have to get a 95% to get an A. There is no universal law of nature that says an A is 95%, though your high school system does make you think that. Right? University exams my exams in particular, are designed to spread the class out so that the A actually is different from a B. Not everybody bunched up between 90 and 100 and then a difference of 1 point. It makes a difference on a letter grade. So expect the scores to be all over the place. I implore you also to look at the grade distribution first before you look at your score. And I think you will have a better assessment of what's going on. I will talk more on Wednesday, and as will the GSIs. All right, so usual schedule. Back to usual schedule. We've got labs. There is no homework due this week. That is unusual, but there will be homework assigned on Friday. Now, today is special. The good people of Microsoft have come to film us today because they are kindly allowing us to use their computing power. The work that you do is, when I say in the cloud, everybody looks up. It's not actually there. It's in some office somewhere. But those are provided to us partly by Microsoft, and they are here to film us just so that they can go back and show their people what is going on in this class that they are supporting. So I do have something to ask. If you do not wish to be filmed, there are rows in the back where we'd like you to go. And I'm going to pause for a second. There is no embarrassment in not wishing to be filmed. It's fine. You didn't come here to be a movie star. Anybody? Anything? Okay, you're on. Do I need to do anything about the mic? You're good? All right, thank you. Okay. So we're going to start with just a quick look back at what we did in the week or 2 weeks before the midterm. We had started on what we call inferential thinking, making conclusions about the world based on random samples. And we had developed a way to decide between two hypotheses about the world. The world looks this way, the world looks that way. And we had a method for making such a decision. Sometimes the question that we want to answer is just much simpler than that. There's some number that we don't know. Say the proportion of people that are going to vote for a particular candidate in an election. This is rather topical these days. Right? There's a number that we don't know. We'd like to estimate it. The question is simply, how big is the number? And so what we're going to do today is talk about estimation. You should recall that we've done this at some level before. Do you remember the enemy warplanes? right? There was some number of warplanes that the other side had, and we were trying to estimate that number, and we had ways, if we take the warplanes that we have seen, how can we estimate that number? And there were a variety of methods that we suggested that we could use, and they had sort of competing good qualities and bad qualities. We're trying to make a guess at a number. So let's make a few obvious points, but that are worth making. Your guess will be based on a sample because you don't have the resources or the ability to go after the entire population. You're trying to figure out a parameter. What's a parameter? A parameter is a what? Sorry? What about the population? When you imagine a parameter, what should you be seeing in your head? A number. That is what you should be seeing in your head. Not an array, not a table, just a number. It is one number associated with the population. So population, in our example, would be the population of everybody who's going to vote in the election, and the number is the percent of them that are going to vote for a particular candidate. That's not a number we know. We might want to try to estimate it. So we would estimate based on a sample, and you know that we will estimate based on a random sample. Why? It's obvious, but say it. You don't want bias. Right? If you take that candidate's 1,000 closest friends and use that as your sample, you will have a large sample. 1,000 is a large sample, but you will be out to lunch. Right? So you will use a random sample. And so what we're going to do today, in fact, this entire week, is talk about making estimates based on random samples. We will be estimating a variety of parameters, such as the population median, for example. We already talked about trying to estimate the total number of warplanes. That's the max. That's a slightly harder problem. We will do median, and the method that we discuss for the median can be applied equally to the mean, which we'll see, and then you can apply it to other parameters as well. The median, we just have been using terms like mean and median subliminally because you kind of know what it is. And that kind of sort of understanding has been fine for now. Once we start to actually doing things precisely, it is important to understand precisely what these terms mean. And so I'm going to take a few moments to do a preliminary about percentiles. It's a little dry, but got to get it done. All right, so the data. You've got a collection of numerical values, and you want the pth percentile. So think P is a number between 0 and 100. How about we do the 80th percentile, right? P is 80. The 80th percentile is a number on the list. It is specifically the smallest value that is at least as large as 80% of all the values, which is a long and involved statement, which is much easier to understand if you simply do it for a list. Okay? Now, you can see on my example, I've got the median of this list, 4, 7, 9, 10, and 15 as 9, and I have a bunch of people who are hyperventilating because their teacher told them it had to be halfway. If you have, well, actually, let me change this to, where am I? No, I want to go back. This 9 is because it is the middle value, right? What I would like to do is to see how that is consistent with this definition that we have given, and then see how this definition is perhaps not consistent with the elementary way people are taught to compute the median. So the 50th percentile, all right. 50%, how many numbers are there? 1, 2, 3, 4, 5 numbers, yes? What's 50% of 5? 2.5. So that's item 1, item 2, there's item 2.5, it doesn't exist. By our definition, so I'm going to put my cursor right there. The median is the smallest item in the list that's bigger or that's at least as large as at 2.5% of the value, 2.5 of these values. All right, so could it be 7 or 4? No, because they're to the left of they're below my 2.5. Yep? Okay, so it's one of 9, 10, or 15. Which is it? It's 9 because that's the smallest one that satisfies that criterion. Yep? All right. So what we're going to do is run through a few little examples. Where am I? Okay, so I've got a dumb array here that I made up, 43, 20, 51, 7, 28, and 34. If you're going to find a percentile is essentially rank order. So arranging the numbers in increasing order is a good idea, and so we do that, and in increasing order we're here. How about we try to find, actually, what's the median? Okay, so we did a definition, and that's just gone out of everybody's heads. I'm hearing the average of 28 and 34. Where in my definition did you see the word average? You did not. In fact, the definition ensures that the number is a value on the list. Yes? So what we need to do is to compute. Let me give myself a cell here. Obviously, 50% of how many values do I have? 6, yes? Okay, there's no career opportunity in doing 0.5 of 6, but I'm going to change that in a moment. So it's the third value that is interesting, 1 to this one. So there's my cursor right there. We want the smallest item in the collection that is at least as large as those 3 values. Which is that? So it's at least as large as that, that, and that, right? It seems to me the smallest value that does that is 28. Yes? Please note, it is not halfway between 28 and 34, like people have been telling you when you were little, because you never asked those people, excuse me, how would I find the 25th percentile? What would that be? A quarter of the way in between something and something else? That is the definition, so-called, it should be in quotes, that is given to people to get a kind of sort of idea of where the median is, right? But we need a definition that works for all ranks and all lists. And this definition is the precise one which, for mathematical reasons, comes out to have the right properties of continuity, etc., etc. So what we're going to do is just develop a way of figuring out what it is if we're just given a list, and then, happily, we have a function that just does it. All right, what I'd like to do is find the 55th percentile of this list. Right? Because you should be able to find any percentile of any list. So I need, what's 55% of 6? So that's 3.3. Okay, so 1, 2, 3, and 3.3 is somewhere here. I need the smallest value that is at least as large as 3.3 of the elements. Which one? So we can check. What's my array called? X. Isn't that a lot nicer than arranging things in increasing order and counting how far up you have to go and then figuring out which one it is? All right. Is that what you got? Yep. So, percentile, our favorite function this week, takes a rank as its first argument, so it's a number between 0 and 100. It takes, listen up, an array as the second, not a table, an array. So there's a table, please do dot column and get out the array, and pops back the percentile according to this definition. Now, the textbook has multiple examples and so on of the use of this function and checking that the formal definition is exactly what this function returns. We don't need to go through that. Just, I think for you it is fine to have just a rough idea when you are using it that it's roughly picks off the 55th percentile roughly picks off the 55-45 split in the data. Right? Note, please, that a percentile is not a percent. It is a value of the variable. It's a number on the horizontal axis. So the 90th percentile is the number on the horizontal axis so that you have roughly 90 below and 10 above. The reason I'm saying roughly is because data sets have ties. You can have exactly the same number over and over again, and then, exactly 90 below and 10 above doesn't exist. So you have to deal with that. This definition deals with that. All right, so apologies for the technicality. It just has to be done. You just now know that if you want to compute the percentile of a list of numbers, you just make sure that those numbers are an array, and then you can use the percentile function. Okay. So back to the problem of estimation. Let me see. So that's your percentile function that we just talked about. It takes a number between 0 and 1 and an array. All right. So we are going to do estimation. As we just said, we're trying to figure out how big an unknown number is. So imagine in your heads a large population. Associated with that is a number. So, all households in the United States, and associated with all those households is, say, the median annual income. What I'd like you to do, please, is in your head, you have that huge population. The parameter that you are thinking of should be one single number, not a number for each household, but one number that is computed out of the entire population. So think of the median annual income of those households. All right, so we want to know how big the unknown parameter is. Well, if I could just take a census, go to every single household, I could just figure out what the median is, and then I would be done. The reason I can't do this usually is because I don't have money. That is classically the reason for taking a sample of a population. You don't have resources to go to every single one. So if you don't have a census, as we said, we are going to take a random, the keyword there is random sample from the population. It doesn't matter how big the sample is if it's not random. You're going to take a random sample from the population, and you are going to use a statistic as an estimate of the parameter. These are all terms that you have seen before. All right. So what I would like to do today is start with a data set that is kindly provided by the city of San Francisco. And it contains employee compensation data for all city employees. I have extracted the bit that is for the calendar year 2015. So we're going to look at all the columns in just a moment, but I would like you to just be clear. There is one row corresponding to each San Francisco city employee in the year 2015. Along the row are various, so this is, calendar year. The other year type, the other was fiscal. I just went with calendar year. It's a little easier for us to understand. The year is 2015, and then there are various affiliations. A department code, which department it is, which union they're a member of, what the job family is, what their job is. This is a water quality tech person, grade 1/2. And then there is the person's salary. Then there's how much overtime, and there's something called other salaries. There's the total, and then there are the benefits. Retirement, health, dental, other benefits, total compensation. We are going to be interested in that last column. All right? So just be clear, we have a population of all San Francisco city employees in 2015. We are interested in the total compensation, and in fact, we are going to be interested in the median, but for now, we're just going to look at the distribution of the total compensation there. And as you can see, there were quite a number of them. Almost 43,000. Okay, just to make sure, actually, before I do the sort, there's somebody you ought to recognize. What's this? Okay, how about trying this? The table is called SF 2015.where job. How about that? That's a job. Let's see. There's Ed Lee. So, job, mayor. It's a job like any other. And there you have a total compensation packet. And before you all start going, ooh, let me give you some comparisons. The principal, the headmaster of the San Francisco Town School for Boys, has something that starts with a 6 correspondingly. So, compensation in San Francisco is of a scale that some of us just don't understand. But anyway, that's the mayor right there. And so, The wonderful thing about public information, this is not hidden. It's out there for data age to analyze. All right. Now, what we'd like to do is look at the total compensation, and I would like you to take a look at what happens when I sort it. The smallest values are a little hard to understand. All right, now this minus, and well, let's take a look. Not only are there minuses, some poor person got paid $1.27. And so this kind of thing happens due to when in the fiscal year, calendar year the person was hired, whether they moved within jobs and so on. There's all kinds of stuff going on. So just for ease of comparison, for us to understand what we are doing, what I'd like to do is focus on employees that we can sort of wrap our heads around, and I'm just going to look at people who had at least a half-time appointment for the full year with at least minimum wage. How does that sound, right? The city can't pay less than minimum wage, right? So if that is the case, then the salary, not the compensation, I'm not talking about the benefits, then the salary should be, let's do this calculation. So minimum wage is roughly $10 an hour in San Francisco in 2015. $10 an hour, half-time is about 20 hours a week, and let's just do 52 weeks. All fine? So that comes out to be about $10,000. And so what we're going to do is we're just going to keep the rows where the salaries, not the total compensation, the salaries are above $10,000. Is it clear why I'm doing that? Okay, so let's take a look at that subset and see. That subset is rather large, by the way. Hold on. So about 36,500 people, so it's quite a large number of people, right? And now in your mind, I would like you to imagine this as your population. The game we're going to play today is we are going to be all-knowing. We have a population, we know its median, we can just figure it out, right? What we're going to do is then we're going to take a sample, pretend we didn't have the population, work with the sample and estimate our median, and then compare. So that will give us some sense whether our method is good or bad. On Wednesday, we will come down to earth and be mere mortals again, and then we'll just have a sample, and the population will be a giant question mark. But hopefully we will have a method where we can see, yeah, this thing works. And then when we use it for an unknown population, we are more reassured that we are using a method that has a good record. Okay, that's the game. Okay, so that's the distribution. Total compensation should come as no surprise to you that distribution has a long right-hand tail. Most of the compensation is, the total packages are below $300,000, and, well, actually, before I do the median, how about, what's the high here? No. High. The poor nurse. I thought he can't possibly be making that much money. Okay, so, that hasn't happened before. Where's my notebook? Much better. Okay, calendar year, general, municipal, chief investment officer. Okay, and chief investment officer, all right, there. All right, the person that manages the money. All right, so that's why I took the bins through to 700,000 in gaps, steps of 25,000. That's all. All right, so what we are going to do is our parameter is going to be the population median. So the median total compensation package is about $110,000 of city employees. All right, so we know that. Now, from a practical perspective, we would never take a sample if you know a parameter, right? You just know it. But now we're going to pretend that we didn't have all the data, and we're going to make a decision based on a sample. All right, so I'm going to shut up. Any questions about the data, the parameter? So we're going to take a sample, which I have reminded myself that I must call our sample. Wonderful. Okay, so SF 2015.sample. You agree? All right, I'm just going to work with a sample size of 500 because that's about the biggest that I can actually simulate here and not have everybody sitting there looking at their watches for the thing to run. Sample size of 500, and just to be... just to sample in a natural manner, I am going to sample without replacement. Does that seem reasonable? If you're sampling a bunch of people, you're naturally going to sample without replacement, so we get our sample. And why don't we take a look at the histogram of our sample. There's the histogram of the sample. Take a look. There's the histogram of the population. Sample. Population. Similar or different? Similar. By what? This is a consequence of something. The law of averages. Yes, if you have a large random sample, then proportions in the sample start looking like proportions in the population, and so then eventually the entire distribution will look like the distribution of the population. We talked about this some time ago. No surprise here. So the good thing is that the sample resembles the population, therefore the sample median should resemble the population median. And that's the hope. We're going to try and use the sample median as our statistic to estimate the population parameter. So what did it come out? Okay, so the estimate of our median, I'm going to use the percentile function 50 because of median. We're going to apply to the table our sample and dot column total compensation because why? Because I need an array and my variable is total compensation. All right, so what do we get? $107,000. Do you remember what the exact value was? About 110. Not bad. Yep. Okay, and now, of course, you are all data scientists, and you're going to say, but it could have been different. And if you're not going to say that, you need to go back and read the last 2 chapters over and over and over again till your eyes pop out. All right, so here we have a little issue. How do we draw another sample? Go back to the population and draw another sample? We can today, but in the real world, you can't go back to the population. You've used up all your resources getting the one sample that you had. You are stuck. So let's just be clear that we know why we're stuck. Okay, so one sample leads to one estimate. Okay, so sample could have come out differently. You know this. You've seen this for weeks. And then the estimate would have been different. So the big question is, how different could the estimate have been? Because you can go with your estimate based on your one sample and dance off merrily, but your conscience will bother you because you know the sample could have been different. Knowing how variable the estimate is will tell us something about the accuracy of the sample, because if that estimate could be all over the place, then you don't have much accuracy. So it is important to get some sense of how variable your estimate is. So you need another sample. And you have a little problem, which is the classic problem that we all have. We have no time and we have no money. Right? We cannot go back to the population to get another sample. So now what? We need another sample. We need something that looks like the population so that we can get another decent estimate from it. Right. So, we need another random sample that looks like the population. We cannot go back to the population. So now we look to see what we have. You are data scientists. What do you have? You have your sample. That's what you have. Those are the data. That sample looks like what? The population. So the brilliant idea of the bootstrap is, well, sample from the sample. Your sample looks like the population. That set of 500 numbers that we drew that we called our sample, that resembles the population. So get another sample from that. Fine, we know how to do that on the computer, but conceptually we have to work out sample of what size? Our original sample had size 500. Yep. If you are going to compare that estimate to the estimate of another sample, how big should that other sample be? Do you recall that the variability of an estimate depends on how big the sample is? Yes, the bigger the sample, the more your sample distribution looks like the population, the better your estimate's going to be. Yep. You've got the median of a sample of size 100, you want to compare with the median of another sample of size 500. You're trying to see how much your original estimate could vary. You need another sample of size 500. From what? From your original sample of size 500. So let's think about this for a second. If you draw at random without replacement, you've got 500 things. If you draw at random without replacement and take them out, what are you going to get as your new sample? This same old sample. There will be no variation, right? This will not be helpful. So the key idea of the bootstrap, and it is a beautiful piece of mathematics that says that it works, is that you sample 500 times. You've got to sample 500 times. You sample 500 times at random with replacement from your sample. That's the bootstrap. And for those of us who are from different cultures, this word, the bootstrap, is a little mystifying. What's it got to do with shoes? Well, there's this wonderful expression that, if you need to get up and you don't have anything else, you lift yourself up by your own bootstraps. So this phrase was coined by Brad Efron, who is a absolutely fantastic statistician, and hence the bootstrap. Maybe if we have time later, I will tell you a story about other cultures now wanting their expressions in because they're really tired of the Americans using terms like there's the bootstrap, there's the jackknife. It just bothers people. Okay. But everyone clear what we're going to try to do, right? We've got a set of 500 numbers that resembles the population. To get another set of 500 numbers that resembles the population, we are going to sample 500 from our sampling. This is why it's called resampling with replacement. Here's why the bootstrap works. This is our population, the same one that's in our example. Here is one large random sample from the population. Law of averages. This one looks like that one, most likely. Agreed? So now, if you sample from this thing, I've done 3, but you can sample as many times. You're sampling with replacement. Law of averages. Most likely, all of these guys look like this. Or the vast majority of those guys look like this. Therefore, most likely, all of these guys look like this. All clear? So we don't have the entire population to sample from, but we've got a stand-in for it. That's our large random sample. And so what we're going to do is we're going to run this process and see what our estimates of the medians look like. And before we actually go to the notebook and start doing the calculation, I would like to take your questions, please, thus far. It's one of the great ideas of statistics of the past century. Brad came up with it in the 1970s, but to do this, you need a computer. You got to draw at random over and over again, and there wasn't that power, and by the late 80s, it was really established. He has a MacArthur Award. Okay. So, resample number 1. What am I going to sample from? Our sample. How many times? 500 times. Now, how many elements are there in our sample? How many rows are there? 500 rows, right? That's how many times I have to sample. It's not up to me. That's how many times I have to sample. Happily, that's the default. If we just do that, it does the bootstrap for you. Right? It takes your table and it samples with replacement the number of times as you have elements in the sample. That's exactly what you ought to do. So before I run that, everybody please note that removing the sample size, you could put it in, of course, right? But removing it will do the bootstrap for you every time. So you're using two defaults here for the bootstrap. You're using the fact that it samples the same number of times as you have rows, and that by default it samples with replacement. Both are important. All right, so resample. That's our resample. And so now this resample looks like what? Kind of. Looks kind of like that, which looks kind of like that. These all look kind of the same. And so if I look at the median of my resampled values, then I should get something. Okay, so I get 101,000. My actual was 110,000. The original sample had what? 107, I forget. Yes? And so this is going to vary. You know that we're going to do it again. And so we're just going to play the same game again. We're going to get resample number 2, which is, okay, sing it out, please. What do I type? Our sample. This, I feel like church. Don't do that. Okay. Now, dot, sample, parentheses. That's it. No more typing. All done. That will give us another sample of size 500 with replacement, and then we will compute the median of that thing. And look, we went above. So we have 113. The actual value was 111. And you can see that some of these are below, some of these are above. Is that a surprise? It is not a surprise. You hope that in the long run you're going to get somewhere around where you want to be. Yep. So we need to do this over and over and over again. What are we going to do? We are going to write a for loop. Do you see why we were doing what we were doing the weeks before the midterm? You're just going to be doing that over and over again. So now we're just going to define a function because we want to do this. So the function is going to be called bootstrap median. It will take 3 variables: the table containing your original sample, the label of the column that has your variable, and the number of replications that you want to do. Okay? So thus far we've done only 2 replications. We've done resample number 1, resample number 2. You have to get a sense of how variable the thing is. We should do lots and lots of replications of that process. Okay, so when we call this function, our original sample, is the name of the table is our sample, right? What will be the label? Total compensation as a string. And then the replications will be however many replications we have patience for. Okay, so what does this do? To speed up the sampling, what I've done is I've just extracted the particular column that we want, rather than carry on the whole big table and sample the whole thing every time. Okay? So there's just one column that we want. I will start with an empty array of medians, and then for each replication we will do. From this one column, we will do a bootstrap sample. You know now why it's dot sample, empty parentheses. Yep. That will give us the same number of elements picked at random with replacement that we call our bootstrap sample. Then we find the median of the bootstrap sample, and we call that number resampled median. And then we append that new resampled median to our medians array. Does this seem familiar? Yes? By the time we are done, you will be writing these in your sleep. Okay? It's the same thing every single time. Now, what does the function return? It returns this object. What type of object is that? It's an array. So let me define the function. I've run the definition. So bootstrap so I'm just going to call that array bstrap median. So what's my function called? Bootstrap median. Okay, first, what do I type? Our sample. Next. And now, 500? No. No, it's how many times I want to repeat the entire process. The sample size has to be 500 anyway. I don't need to tell it that, right? We did resample 1, resample 2. We could have done 3, 4, 5. We could have done that process over and over and over again, right? I've just, in the interest of time, I'm only going to do 5,000. You should probably do 10. Okay, so what has to happen here? For each of 5,000 times, the following has to happen. This thing is going to draw 500 times with replacement from our sample and find the median. Yep? All right. So if I run this, I think you can see it takes a little time, not a lot, I hope. So there's my star. Done. That didn't take long. 5,000 resamples, and so now I put them in an array and draw a histogram. Okay. This red dot is the actual value, right? In real life, you will not know where that red dot is. Today, we are all knowing, we know where it is. I put it down there, right? Okay, this histogram is composed of how many values? 5,000 values. There are 5,000 sampled medians. I should say 5,000 resampled medians. That's the distribution. What is random here? Is this red dot random? The red dot is not random. And here, in your head, you should somehow label what's fixed and what's moving here. The red dot is fixed. I want you to imagine it as a nail that has been hammered into the number line. It is the population median. It happens to be $110,305.79. There's nothing, you cannot mess with that. That's a number. So what's random? It's that histogram that's random. Right? That histogram can slide around depending on how your samples came out. Right? And you are happy with that histogram if it kind of sits on top of your red dot. Because if it doesn't touch your red dot, or only kind of brushes your red dot, your estimates are mostly off. You agree? And here you see that it's not right here, but it's somewhere in the bulk of the distribution. And so now the question is, how do I define sitting right on top of the distribution? And I'm going to do something here that I don't usually do. I'm going to go to another notebook, and I am going to run something. You see this thing called the big simulation? I will show you what it is later. I just want to show you that I'm actually running it here. It's not cheating. I'm going to run this simulation here because it takes forever. I'm just going to run this cell. That star is going to be there for a lot of minutes, and we're just going to come back to our discussion. And everybody's going, what was there? It's coming. It's coming. Okay. Okay, so now what we're going to do is we are going to give a definition of what it means for that histogram to be kind of sitting firmly on that red dot, because that's what you want, right? A traditional definition that is used is, and again, this is conventional, but a traditional definition that is used is the middle 95% of your distribution contains that red dot. So let's think about what middle 95% means. Right? From here to here, it has to be 95% of the data. In this case, the left endpoint should be what? If you want the middle 95%, right, what percent are in the two tails? 5%, and if you want to do that equally, you don't have to, but if you want to do it equally, we're going to, right? Then you should have 2.5% on either side. Yep, you see percentiles again? The 2.5th percentile is one of them. And what's the other? The 97.5th percentile. You have to subtract 2.5 from 100. You agree? So the middle 95% is an interval that you will get. So here I am finding the left endpoint of that interval, and that's 101, and I am finding the right endpoint of that interval. That's 113, and happily for me, this 110, which is my red dot, is sitting in the middle there. Yep. So I think what I did was I drew the histogram again with that interval colored for you. Now, there's graphics commands in these cells. You can ignore them for now. If you read the graphics commands, they're actually not that difficult apart from colors and so on. If you're interested, just talk to your GSI. That's not something we're going to expect you to know. Okay, but what I want you to understand very thoroughly is exactly what has been drawn there. What's been drawn there is this is your bootstrap empirical histogram of 5,000 resampled medians All agree with that? Okay. The red dot is the actual population median. That yellow interval is this middle 95% of all of these 5,000 medians, starting from the 2.5th percentile to the 97.5th percentile. Right? It picks up where 95%, the bulk of those resampled medians are. And we are going to define our interval to be good if that interval contains a red dot. Otherwise, it's a bad interval. Right? This interval happened to be a good one. So obviously, there's the question of, well, if we had done this whole thing again, wouldn't we have got a different yellow interval? Yes, because that empirical histogram would have been different. The red dot would have been in exactly the same spot, but the histogram would have moved. So we'd have got a different interval which may or may not have contained the red dot that we are trying to get it to contain. Yes? That is why I'm running the other cell. And I will now go... Okay. What this is doing is it is doing 100 times what we just did. It's going to compute 100 intervals, and this thing takes it's done. Perfect timing. Yes. Okay, so let me show you what it produced. These are the intervals that it produced. It produced 100 intervals. Yes? Left end, right end. And what we're going to do is we are going to count where the left end is below the population median and where the right end is above the population median. Yep. Okay. 94 of them. The process is good approximately 95% of the time. Okay? And therefore, this is a process that we will use Wednesday onwards to estimate numbers. All right, more to come. I'll see you Wednesday.